Hi everybody, Dr. A here, and in this video we are going to be giving some background information on maximum in-plane shear stress on a stress element. So similar to our discussion in our previous video, we can actually transform an element into an associated element subject to maximum shear stress with an associated average normal stress. So our previous video talked about maximum normal stresses, which we called principal stresses. In this video, we're talking about a maximum shear stress, like a tau max that comes from transforming your element into a different state that has an accompanying maximum shear stress. So how do we do this? Well, to transform an element into a state of maximum shear stress, we use the following relationship. We say tangent of 2 theta s equals negative, open parentheses, sigma x minus sigma y, all divided by 2 times tau xy. Now this tangent equation is very similar to the one we saw in the previous video regarding principal stresses, except in this equation we are calculating two theta values, theta s1 and theta s2, that will define our stress element that's subject to maximum shear stress. So let's write this down. So theta s actually represents two angles, theta s1 and theta s2, that are complementary angles and define the orientation of a transformed element sustaining, see if I can spell correctly, sustaining a maximum in-plane shear stress, which we call tau max. Now the question is, how do we calculate tau max? Well, it turns out tau max is going to be equal to just plus and minus the square root of sigma x minus sigma y over 2 squared plus tau xy squared. Okay, now it turns out we are going to have an associated average normal stress on this transformed element. So if you remember from the previous video, when we discussed principal stresses, the associated shear stress on the transformed element was what? Well, it was 0. That's not the case here. When we're talking about a transformed element where we want maximum shear stress, tau max, you are going to have an associated average normal stress on that transformed element. So what that is going to be is the following. We're going to say there is an associated average normal stress, which we call sigma average, on this element. And this is simply given as sigma average equals sigma x plus sigma y over 2. So again, graphically, what are we doing here? Well, let's go ahead and draw some global x and y coordinates. So graphically, we have a stress element, okay, very similar to what we've seen a few times now in the other videos, where we have a sigma y, we have a sigma x, oh, sorry, that's not sigma x, that's also sigma y. We have a sigma x, we have a sigma x, and then we have a tau xy here, and this is going to be transformed into an equivalent system. So I'm going to just immediately go to the transformed y prime x prime coordinates. So the transformed equivalent system is going to have a tau max acting on it, but it's also going to have an associated average normal stress. So we're going to sketch that on like this all around. Okay, so that's it. That is going to conclude this video. Again, you see there's a lot of parallels between how we calculate the maximum shear stress state to how we calculated the maximum normal stress state, which we call principal stresses in the other video. So it's important to not get these two confused. You are actually doing two different but similar processes. So that concludes this video. Please hit like and subscribe.